Okay, yesterday we started the discussion of what purity means when we're talking about chemical compounds. Um, and I said today we'd look at some specific situations. So, one specific situation where we want to analyze the purity of a compound um, might have to do with a hydrated salt. You've seen some examples of hydrated salts on problem sets before. We may have talked about it here or there, but I want to explicitly talk about what a hydrated salt is. Um, so a hydrated salt is when you have an ionic compound, and we know in an ionic compound that generally there's going to be a repeating pattern of positive and negative ions. So when we think of ionic compounds, normally we think of plus, minus, plus, minus. We think of a pattern that looks like this. And I hope that I've pounded that idea into your head enough at this point. When you hear ionic, you kind of see that picture. With a hydrated salt, what happens is in between those ions, there are actually going to be water molecules. So I'll draw them in as little red things here, and then I'll show you a better representation. So with a hydrated salt, you've got water molecules embedded in between the ions. Um, so here is a three-dimensional representation of it. Come on, zoom in. So in this picture, I've got my positive and negative ions. This one happens to be a representation of copper 2 sulfate pentahydrate. So what copper 2 sulfate pentahydrate means is that in that crystal, for every one formula unit of copper 2 sulfate, there are 5 water molecules embedded. And every hydrate has a different number of water molecules. So here, the water molecules are shown in the tube structures. So this little white part would be a hydrogen, the red part would be the oxygen, the white part would be hydrogen again. These red ions would represent the copper 2 plus ions. And then you see the polyatomic ion, the sulfate ion. Yellow here is sulfur, and then there are 4 oxygens around it to make the sulfate. Okay, so these would be ionic compounds that are a little more complicated. It's almost like the water has dissolved into the solid. But it usually dissolves in a specific ratio. So when you have copper 2 sulfate, when it gets hydrated, it absorbs 5 water molecules per formula unit. There are others like copper 2 chloride that absorb 2 water molecules per formula unit. Others absorb 6 water molecules per formula unit. But you get this structure where in between the alternating positive and negative ions, you have water molecules. Okay. What questions do you have about the structure of a hydrate? Yep. The question is, what state of matter is it? It would be a solid. So this would be in the crystals. So, for instance, people doing the analysis of brass lab used copper 2 nitrate. That was trihydrate. So for every 1 formula unit of copper nitrate, there were 3 water molecules embedded. And it's a solid. It's crystals. Yep. And let me. All right. So the question is, why would something like this happen? Well, water, remember, is going to be strongly attracted to ions. And so if you don't put this in water, but you let it just absorb water from the air, it's not going to become a liquid. It just absorbs enough water to surround the ions like this. So it's a tiny amount of water compared to the amount of water you would dissolve it in, say. Yep. Another question? So the question is, are all salts hydrated? No. Only certain salts get hydrated. Only certain salts get hydrated in a specific ratio like this, where they stay solid. There are other salts that will absorb some water from the air, and you can tell that if you have salt that starts to clump together, that it's absorbed some water from the air, but it's not always in a specific ratio like this. So hydrated salts specifically are ones that absorb a specific number of water molecules per formula unit. No, I don't want to change my colors. All right. I guess I'll close that. So in the lab, hydrated salts allow us to do some interesting analysis, because you might imagine if I heat a hydrated salt, what might be the first thing that happens to it? Stops being a hydrated salt. You can drive the water molecules out. It takes a lot less thermal energy to drive the water molecules out than it does to actually make the ionic compound itself melt or break down. So you can drive the water molecules away by heating, and that can give you a way to analyze a hydrated salt. So these are just some examples of hydrated salts. Copper 2 sulfate pentahydrate, this is the one that I just showed the model for. So this has 5 water molecules per formula unit of copper sulfate. Cobalt chloride, turns out, is a hexahydrate. So that has 6 water molecules. So based on knowing the formula of a hydrated salt, you can figure out what the mass change should be when you heat it. All right. So here's an example of how we might analyze the purity of a hydrated salt. Suppose you take a certain mass from a bottle labeled copper 2 chloride dihydrate, CuCl2.2H2O. You heat it several times and weigh it after each heating. We talked yesterday about why you might want to do that. Why would you heat it several times and weigh it several times? Adriana? To make sure that it's been heated completely, that you heated it enough to drive off all the water in this case. If you see the mass come to a constant value, that tells you, okay, there's no more water that I can get out of this. All right, so after the 3rd and 4th heatings, the mass stays constant at 1.683 grams. Do you believe that the sample is pure copper 2 chloride dihydrate? Justify your answer. Now, before you embark on trying to come up with an answer, I do want to point out these formulas have a dot in the middle. And sometimes people are programmed from math to think a dot represents what? Multiplication. When you're figuring out the molar mass of a hydrate, would it make sense to multiply the molar mass of cobalt chloride or copper chloride by the mass of the water molecules? No. The dot means something different here. The dot just means they are embedded in the crystal. So when you're figuring out molar masses, you add them together. You don't multiply them. You do multiply 6. So in this case, you would, of cobalt chloride, you would say 6 water molecules, so you would multiply the molar mass of water times 6. But you're not then going to multiply that by the mass of cobalt 2 chloride. because you're just adding those water molecules in. So go ahead and try and answer that question. Work together at your tables. All right, who wants to explain their approach? Benny? All right, you started with the given mass of the hydrate, 2.133 grams. All right, so first assumed that it was pure and calculated what? So you figured out how many moles of hydrate it would be. So you converted grams to moles. Then then said, all right, there's a 1-to-1 ratio between the hydrate and the non-hydrated stuff that should be left at the end. And then multiply that by the molar mass of just copper chloride itself. So the idea is we started with the hydrate. We should end up with pure copper 2 chloride. And we want to see, well, did we end up with the amount of copper 2 chloride we'd expect? So as a calculation, that looks like this. You start with your mass of copper 2 chloride, use the molar mass to change it to moles. Molar ratio is 1-to-1, and then multiply by the molar mass of the unhydrated salt. So what mass does that give you? 1.682. So this is expected mass of CuCl2 if the sample was pure. All right. Now let's compare that. What mass did we actually get? 1.683. All right. So, do you believe that the sample is pure? How do you say yes? Why? Came out to just about the same value. Now, some people asked, well, is it okay if it's 1.683 as opposed to 1.682? What do we say about the last digit? There's always uncertainty in that last digit. So we're definitely within the range of uncertainty. This certainly could be pure. We don't really have any evidence to say, no, it's not pure. There are judgment calls in real life, so you can't always just ask me like, oh, is it okay if they're like this? You sometimes have to make a judgment call and say, you know what, those two are close enough that I think it probably is pure. You recognize that, you know, there's all sorts of possibilities. It might be impure, but I might have impurities that, you know, lost the exact same amount of mass, though in the exact same ratio or something like that. But we don't have any evidence that it's not pure, I would say. So, conclusion. There's no evidence that the sample is impure. We can't say we proved that it's pure, but we can say we didn't prove that it's impure. So the question is, would it ever be the case that the ratio in this, if we had a calculation like this, that this ratio here would not be 1-to-1? No, because if you drive the water away, you leave behind just the salt itself. So since there's no other reaction going on, this will always be a 1-to-1 ratio. All right, what questions do you have? So the student question is, will the question always tell us what the ratio is in the hydrated salt? The answer is no. I mean, anything about this problem could be the missing variable that you have to solve for. So, for example, you could have a problem that gives you the initial mass, gives you the final mass, tells you to assume that it was a pure sample, and asks you to figure out what the ratio is, so how many water molecules there are. So, yeah, you can come at this analysis from different perspectives. But this is a classic one, and I think it's one that will be part of our next Choose Your Own Adventure lab, where some people might have to figure out the ratios in some different hydrated salts by doing this in the lab. The reason this is kind of a classic question for the AP test or for general chemistry classes in general chemistry classes in general. Sorry to be repetitively redundant. But the reason this is such a common question is it's a very easy thing to carry out in the lab. You can go in, heat it, weigh your sample, compare, and get a result. And so that's why the questions show up on the AP tests from time to time. All right, let's take a 3-minute break to do whatever you want to do. So now we're going to look specifically at some lab techniques that you will need to be familiar with. So it's going to be a bunch of terminology. The underlying problems are all just stoichiometry problems, but you need to be familiar with some of the terminology, be able to read a procedure that would go along with one of these kind of experiments, and then analyze the data. Okay. With the new AP test, a lot of what they do is not expect you to have memorized a procedure, but they'll describe a procedure. And so you've got to just be familiar enough with the vocabulary to understand what they mean when they say, a student performed a titration. Or my favorite is the gravimetric analysis. I had never heard that term until, I don't know, a few years back. Actually, I guess I heard that term when I first started teaching AP Chem, but I was like, why do you need a fancy name for that? So we'll explain what these are, but we're going to talk about 3 techniques. One we've already discussed kind of in detail. That would be using absorbance measurements. That's what we call Beer's law. Gravimetric analysis, which would be when you do a precipitation reaction, then you filter and dry the product, and then weigh the product. And then a titration. So that would be when you take a solution for which you know the concentration, you add it to another solution for which you don't know the concentration, and you have a reaction happen, and use stoichiometry to figure out the concentration of the unknown solution. All right, so what do we remember about Beer's law? First of all, I prefer the name Kool-Aid's law. I think you may remember I may have said that in the lecture that you watched over the summer. I think it was in one of those first lectures. What's Kool-Aid's law? All right. Have you ever mixed your own Kool-Aid or Gatorade or any drink from a mix? All right. What are the ways you can make the solution darker? All right, you could add more mix to less water. So in other words, you could add a higher concentration. So one of the things that affects how much light a solution absorbs is going to be what the concentration is. What's another way you could make it appear darker? All right, so yeah, one way you could adjust the concentration by either adding more mix or less water. Um, what about the container it's in? If you look at it through a pitcher versus looking at it through a little glass, when does it appear darker? All right, not a lot of people have this experience, I guess. But when you take the Kool-Aid and it's in the pitcher, and the light has a long way to pass through, if you pour it into a little glass where the light has less way to pass through, it appears a lighter color. It absorbs less light. So what Beer's law essentially says, and this is on your formula sheet, and it's in this really silly form on your formula sheet. It says A equals ABC. And this is just someone's idea of, oh, wouldn't it be cute if we had an equation that said A equals ABC? So let's do that. So this is how it appears on your formula sheet. Actually, I should confirm that. Take a look at your formula sheet. A equals ABC. Yeah. Now the parts of this equation, capital A is absorbance. Absorbance is something you can measure using a spectrometer. We've done this everyone's done it at least once. The people who did the brass analysis lab have done it again. This is equal to the negative log of the transmittance. But the good news is you never have to think about transmittance again, because the data you'll always be given will just be absorbance. So A is absorbance. Now in the equation, C is the only one that makes sense. What do you think C represents? Concentration. So C equals concentration in moles per liter. All right, so C is really molarity. But then A and B, they just kind of shoehorned those variables in there, and they have no correspondence to what they represent. Maybe you could say little a does, but B is what we call the path length. So this is how far the light has to travel through the solution. Now, when we do experiments in the lab, what do we do with the path length? Do we change the path length? No, we keep it constant by using a cuvette of the same size the whole time. So really, this is always going to be held constant in our experiments. And then little a, what little a represents is the fact that, if you use a different flavor of Kool-Aid, it's going to absorb a different amount of light at each wavelength. So little a is called the molar absorptivity. Back when I learned Beer's law, it was actually Greek letter E. It was epsilon, and it was called the extinction coefficient. I don't know why they decided to change the name of it. But the molar absorptivity is essentially a property of a given compound at a given wavelength. So in an experiment, if you're using the same compound and you're using the same wavelength, what can we say about molar absorptivity? It's also held constant. So what this equation really boils down to is absorbance equals a constant times concentration. So it means absorbance should be directly proportional to concentration. So we can use that to our advantage by taking solutions for which we know the concentration, measuring their absorbance, determining what this mathematical relationship is, and then for solutions where we don't know the concentration, if we measure their absorbance, we can determine their concentration. So let's all practice that one more time. So suppose you made solutions of a red dye of known concentration and measured the absorbance of each one at 565 nanometers. Those results are plotted here. I think for you they're on another slide. But what's the concentration of the red dye solution that has an absorbance of 0.375 at 565 nanometers? So you go through the trouble of measuring the absorbance of a bunch of different known concentrations. You make this graph. How would I determine the concentration of a solution with an absorbance of 0.375? All right, one way would be to use the graph and just draw lines. All right, so absorbance is on this vertical axis. So what I might do is say, all right, 0.375 is about right here. And so if I trace that across to where it meets the line and then go down, I can get an estimate. So my estimated concentration would be about what? I'm going to say, based on my rough drawing of the lines, I'm just going to say it's somewhere around 0.07. So that's a way to get an estimate. What would be a way to get a more precise answer? Lena? All right, so I'm given an equation here, and that equation, essentially y in that equation represents absorbance. So really this is A, and then x represents concentration, so this is C. Remember what we said was Beer's law boils down to A equals a constant times C. So essentially A equals that constant times C. So I could plug in 0.375 for A. So 0.375 equals 5.3645 times C. And then I could just solve for C. So it would be this. Divide both sides by 5.3645. And I get 0.069. So the question is, how come we're not taking into account B, the path length? Well, in an experiment, you would use a cuvette, the same cuvette, so it's going to have exactly the same path length every time. So that's a constant. Essentially, the slope of this graph is representing little a times b. So the slope of this graph represents the path length times the molar absorptivity of the compound. So the question is, do the values of A and B have units attached to them? Yeah. So B would generally be in centimeters or something like that. And then A would be, well, we can figure out what the units are. If this absorbance is unitless, so concentration is moles per liter, so the constant has to be in liters per mole. And if you break it into A and B, if B is in centimeters, then A would have to be in liters per mole centimeter. They're weird units, but they do exist. So the question is, could you look up the values for A, for molar absorptivity for a given compound, and just skip the whole graphing part? The answer is maybe. You may be able to look up those values. I think it's usually more advisable in any experimental situation to determine the constant independently, like in your own lab setting, because with your equipment, with your individual cuvette, there are always slight variations, and so you're always going to be better off taking the approach where you make the graph, figure out what the constant is on your own. But in theory, those values of little a are constants for a given compound at a given wavelength. So you could probably look them up. You might have to dig. Yeah. Other questions? All right, let's take another 2-minute break. Would be gravimetric analysis. And like I said, this is really one of these cases where someone just wanted to throw a fancy word on there to make themselves sound smart. Kind of like stoichiometry, gravimetric analysis. I mean, any idea where that name would come from? Gravity. Oh yeah. So basically this means analyzing by weighing, right? That's essentially so it's a fancy way to say we're analyzing something by weighing it. But the overview is you take a solution of unknown concentration and you precipitate out the ions. So this only really works for ionic solutions, because then you're going to carry out a precipitation reaction to remove all of one type of ion from the solution. So for example, if you were analyzing a silver solution, if you were analyzing a solution of silver nitrate, which of those two ions are you likely to be able to precipitate out? The silver. Why not the nitrate? Nitrate always dissolves. Nitrate's unlovable. No one's going to take nitrate off the dance floor. So, to analyze a solution of silver nitrate, you might add sodium chloride. And then the silver and the chloride could fall in love. And come out of the solution. Now, once you got those ions out of solution, how could you separate them from the water? How can you separate a solid from water? All right, so one possibility would be to heat it. Now, if you heat it and you evaporate off all the water, what's going to be left behind? All of the ions, right? So even the ones that were dissolved would end up staying behind. So we're not gonna separate by heating, because that would leave behind all the ions. I just want to figure out how much of this precipitate is there. So how could I separate it from the water? Filtration. So the next step would be filter the mixture and then dry and weigh the precipitate. Once you know how much precipitate was there, you use stoichiometry to figure out what the concentration of the original solution was. Oh, not mass of the original solution, concentration of the original solution. And I'm going to make no claim to the next problem. The next problem was written by Mr. Bennett, so I'll give him the credit or the blame, depending on your perspective on that problem. Okay, Paul Bunyan, PB, was concerned about the level of lead, PB, in the water that his ox Babe was drinking. Babe was more worried about the barium content. All right. In order to analyze the lead content, he takes a sample of the water and concentrates it 100 times by distilling off 99% of the original volume. A lot of times to do a gravimetric analysis, if you have really dilute solutions, if you want to get a measurable amount of precipitate, you need to make it more concentrated. So you can actually distill off some of the water. So then he takes 25 milliliters of the concentrated sample, adds an excess amount of 0.1 molar sodium iodide solution in order to precipitate out all the lead ions as PbI2. Filtered the precipitate, dried it, and masked it. This data is recorded on the next slide. So the mass of the dry filter paper was 13.65 grams. The mass of the filter paper plus the precipitate was 1.893 grams. And the question is, all right, what is the lead ion concentration in that original solution? Who's got ideas on how to approach this from a stoichiometry perspective? What's our plan? Our plan is to sit silently and wait for someone else to answer. All right? We need a chemical equation. So what would the chemical equation be? Well, we had a solution that had Pb2 plus in it. We're just going to skip right to a net ionic equation. If our solution has Pb2 plus in it, what is that Pb2 plus going to react with? Iodide. How many iodides? 2. That's going to make my PbI2 solid. All right. Now, what can I figure out the mass of based on the data? Which of those things do I have data to determine how much of it was there? Chris? PbI2 solid, because the precipitate is PbI2 solid. We have the filter paper alone, the filter paper plus the precipitate. So we can use those two to determine what the mass of PbI2 is. How many grams of PbI2 is there? 0.528 grams. All right. So now we're somewhere. With stoichiometry, we always need to take our given quantity of something. And then once we have our given quantity, Livy, I just saw you mouth. What do we do with it? Make it moles. All right. So we're going to turn that into moles. So we're going to take grams of PbI2. We're going to turn that into moles of PbI2. All right. Now really, what are we interested in? What are we interested in finding? Not how much PbI2 was there, but how much what was there? Pb2 plus. Okay. So we can go from moles of PbI2 to moles of Pb2 plus. That's going to be pretty straightforward because in the equation it's a 1-to-1 ratio. Most times with these precipitation reactions, you're going to end up with a 1-to-1 ratio, which makes life a little easier. And then we weren't asked about moles. We were asked about what? Concentration. So we're going to have to turn moles of Pb2 plus into moles per liter of Pb2 plus. So these analysis questions, they're really stoichiometry questions, but you've got to dig through the data a little bit to get your relevant starting point. So go ahead, figure out the concentration in Babe's drinking water and see if Babe is maybe suffering from lead poisoning. All right, I sketched out my answer, but I need you to help me fill in numbers. So to get from grams to moles, we need the molar mass of PbI2, which is, Giovanni? 461.02. All right, the .02 isn't going to end up mattering because that's out in the fifth sig fig, but all right. So that leaves me with how many moles of Pb2 plus? 0.001145. All right. That's in 25 milliliters of the concentrated solution. Notice the 0.1 molar sodium iodide, that 0.1 wasn't relevant to us because we were using an excess of that solution. So in the problem, there's this 0.1 molar that we don't end up using. That's just going to distract you. So don't think that every number in the problem has to be important. Because we're using an excess of the sodium iodide, it really doesn't matter what concentration it was, because we're just adding more and more of it until it stops precipitating. but it is in 25 milliliters of the sample. So to get the concentration, I would take my 0.001145 moles of Pb2 plus and divide by the volume. Which was 0.025 liters. And that gives me what concentration? 0.0. There's another zero in there, isn't there? 0.0458 moles per liter. All right. Now, that was the concentrated solution. That was after we had reduced the volume by a factor of 100. So the original solution would be 100 times less concentrated. So that would be, let's say, 4.58 times 10 to the, this was -2, so that would be times 10 to the -4 moles per liter. And I don't actually know if that's an acceptable or an unacceptable concentration of lead in drinking water for an ox. All right. What questions do you have about gravimetric analysis? Sweet. Then we just have one more technique to talk about, I guess. I think we're going to do that next Tuesday, a week from today, because we don't meet on Thursday, and Friday is the day before the test, so I want to have that day to do some review. So I think, yeah, we'll cover titration next week.